This is lecture 9.8, the final lecture in our acid-base equilibrium unit, and is kind of a adjustment from lecture 9.7, which was weak acid, strong base, and this is weak bases, strong acids. So the learning targets are kind of short, and you can probably get a pretty good foundation from this just from comparing what would change between weak acids and strong base titrations when you start with a weak base and titrate with a strong acid. So try on your own to kind of outline the steps, etc. Before you even use your book. You should have a sketch of the curve, etc., and then you can restart the lecture. So here goes. A weak base strong acid titration has some similar characteristics to a strong in that it has this vertical location, or this vertical section, where the center of that vertical section would be your equivalence point. And it's similar to a weak acid strong base titration in that the beginning of it here, anywhere basically from just having added some of your titrant to getting to the point where you are just before the equivalence point, that all of that region is technically a buffer. So when you're calculating, you can use Henderson-Hasselbalch as long as you're in that region. So there are definitely some similarities. Notice that the pH starts above 7, but not as high perhaps as a strong base would start. We would maybe expect, if this was a strong titration, that it would start somewhere up around 12 or 13. So it's starting a little bit lower. Also notice that if this were a strong titration, it would stay at a higher pH for longer and then drop all at once and kind of look like that. So this is a way that we know that we have this buffer, is that the pH lowers kind of steadily for a little while and then drops all at once. The similarity for this in a strong titration afterwards, after the equivalence point, is very similar. Remember that now we have the excess of our strong acid, and so the pH will drop drastically at that point and stay low, because the adding of that strong acid just kind of keeps it really low. At that point, you're not really creating a buffer at all at that point. And you do have some of the conjugate base in there, which is why it doesn't drop any farther than that. Okay, so so this is the characteristics, and you should be able to identify what's there in all of those regions. Now let's look at some titration calculations. I'm not going to talk through these much because it's very similar to what you saw when you were titrating a weak acid with a strong base. The difference is that now you have your sorry, this is a typo in here that I just noticed. Before beginning, you have only the weak base in the flask, and you're using the initial molarity of the weak base and your ice chart, and this would have to be a base dissociation equation. So you'd have to do your weak base plus water at equilibrium with the OH minus ion and the conjugate acid, right? So this is kind of what you're looking at. And then from there on, it's very similar. Before equivalence, you have a buffer. So you're using Henderson-Hasselbalch. If you're at equivalence, then what you have left is your conjugate acid. So you need to find its molarity and ice it to find its pH. If you are exactly halfway to equivalence, this is the same, where pH is pKa. And if you have excess strong acid left, remember that your equation for your titration would be weak base plus H plus, and it's going to end up equaling the compound, usually weak base H plus together, right? So that's kind of weird to put it like that. It'd be better for me to write it the way that we usually would write it, which would be B minus plus H plus gives us HB, right? So if your weak base is limiting, then you have excess H plus. You also have a weak acid there, but we're going to ignore the weak acid because having that strong acid prevents it from ionizing very much anyway, and it will be beyond our significant figures. So here's the idea. If I were you, I would stop the video and try this on your own. I'm going to give you the answers to these before we go any farther, and you can check your answers. And then if you don't need to watch the rest of the video, this one I've allowed you to fast forward to the end from this point forward. Okay, so I'll give you answers and you can kind of see where you stand. The answer to A is 11.86. The answer to B has a pH of 10.72. C has a pH of 10.24. F has a pH of 6.01. And G has a pH of 3.9. Okay, so if you have correct answers, then you can go ahead and fast forward. Otherwise, you are welcome to watch the rest of the video and kind of figure out what's going on. Okay, so just like every other titration, what I did is set this up by finding the points of reference for myself before I went any farther. So my points of reference will be the moles of my analyte, which is the triethylamine that's in the flask. So I'm just going to call this moles of, well, at this point I'll write it the way it is, CH3, CH2, 3N. And I'm going to find that from volume times molarity. And that would be, put this in liters, so 0.02000 liters times 0.1000 molar. And that is 0.00200 moles of weak base. Okay. And then I'm going to figure out the volume of my HCl to add to get to equivalence, because I want those reference markers here so that I can kind of predict what's happening. So that's going to be Vm equals Vm, one for the acid, one for the base. So that would be, again, my 0.02, the acid is what I'm looking for. And the molarity of the acid is 0.1 molar. And the volume of the base was 20 milliliters times its molarity, which is also 0.1. Okay, so this tells me now, notice that these have the same molarity, so I'm going to need the same volume because they're both one hydrogen, one hydroxide. Remember that it's always a good practice for your hydroxides to put that in there, but in this case it's not a strong base, so it doesn't matter. So the volume of the acid needed at equivalence is going to be 20 milliliters. Sorry, I'll put this in the way it came out, which would be 0.02000 liters, or 20.00 milliliters. So this is my frame of reference. So now I can look at this and I can come up here and say this one in F is at equivalence, and this one here is past equivalence, and all of these are before equivalence, and this one, by the way, is at half equivalence. And so this is a really good frame of reference to know. The other thing that I'm going to do is go ahead and write the equation, which would be CH3, CH2, 3 of them. There's my triethylamine plus H plus yields, actually I'm going to move this so that it's kind of easier to see, yields CH3, CH2, 3 of them, NH plus. All right, so this weak amine is going to hang on to that hydrogen ion. So this is my titration equation. And so I can see that before equivalence, what's going to be left at equivalence, right? I would have my weak base left, or my weak acid left, or produced weak acid isn't going to be there. And so I would have to worry about that. This means that I'm going to choose an indicator that changes in an acidic pH, like perhaps methyl red is a good choice. So things like that I can come up with from that basic information. So now let's go ahead and get started. A is before titrating. And so this is my weak base only. So I'm going to put my weak base, I'm going to change what I call this. I'm going to call it XN, right? Because maybe I'll do it this way, because I want this to be something that's way faster for us to write. So I'm going to call it Bn because it's a base, and I'm going to add my hydrogen ions to it. I'm sorry, in this case, before I'm titrating, this is my base in water. So at this point, that's going to give me this is going to accept the hydrogen, so this is going to give me the hydrogenated version, which will be this version, and leave behind OH minuses. And if that confuses you, then come back in and rewrite this as CH3, CH2, N, three of those, NH plus, right? Because I just am getting lazy because it's taking me forever to write all that. But technically now this is a weak base, so I'm going to ice it. I was given my initial molarity as 0.1 molar, and remember this has to be in molarity, capital M. So this was 0.1 molar. I'm not worried about the water. There's neither of those. This is going to be 0.1 minus X. These are both plus X. And now I can use, this is a base, so I'm going to use KB equal to, they told me 5.2 times 10 to the negative fourth. And that equals X squared over 0.1 minus X. And I'm going to cross off the X. I'm going to cross multiply and solve. X will be OH minus, and I get an OH minus of 0.0072111026. Now I noticed that this is actually a pretty large number, so I checked percent ionization. Percent ionization would then be the 0.007211, etc., divided by my initial concentration, which was 0.1 times 100 to make it a percent, and it actually is 7.2% ionization. Technically, I need the quadratic, but I don't care. I'm going to do this without it because I don't think that the College Board would make you do that. So I'm going to continue on knowing that my error is large and that it would really matter, but at this point we don't care. So we're going to do POH is the negative log of OH minus, and that gives me 2.141998, a bunch of numbers. pH then is 14 minus the POH, which is 11.85800, more numbers. And I have two significant figures using KB, so this would be 11.86 as a starting pH before I begin. So this is before I add any strong acid to my weak base. All right, part B is after adding some strong acid, and I noticed when I was looking at this that this is halfway to equivalence. So I'm going to use the shortcut for half equivalence. At halfway to equivalence, pH equals pKa. And so I don't really even need my BCA chart, etc. I'll show you that one in part C, but I can just do this. So pH equals, now I don't know pKa, so I need to do the negative log of 1 times 10 to the negative 14th over Kb, which was 5.2 times 10 to the negative 4th. And that gives me 10.716003, which I'm going to round to two significant figures from the Kb, which will be 10.72. Remember, the only reason I'm allowed to do this is because I've added half as much H plus as the weak base present. So basically what happens is that in my BCA chart, I have half of my weak base left, and I've created an equal amount of the conjugate acid. So in Henderson-Hasselbalch, the term that would come after this, which would be the plus log of weak base over conjugate acid, this equals 1. And so because of that, the log of 1 equals 0, and I can just do pH equals pKa. All right, part C. Now we've added 15 milliliters of HCl. This is definitely not to equivalence yet. I decided that equivalence was at 20 milliliters. So this is going to be a situation where I need to know moles and I need to do my BCA chart. So moles of HCl will be 0.01500 liters times its 0.1 molar gives me 0.001500 moles. And now I'm going to set up my BCA chart. So this will be H plus plus, I'll write it all out, CH3, CH2, 3 of them, N gives me CH3, CH2, 3 of them, NH plus. And my BCA chart, this is going to be in moles now. I'm trying to figure out who's in my flask and how much of it. So this will be 0.001500. The moles of my weak base that I figured out in the very beginning, remember, is 0.002. So this will be 0.00200. I forgot how many zeros. 3 zeros. And I have none of this. This is my limiting. My H plus is my limiting. So minus 0.001500 minus 0.001500 plus 0.001500. This is easy. This gives, this gives me 0.001500. This gives me 0. This gives me 0.000500. You have to be really careful. But notice that what's in my flask is my conjugate pair. So this is a buffer. So I'm going to use Henderson-Hasselbalch. And that's because I have concentrations of both of my conjugate pair. So this would be pH equals the negative log, again, of Ka. I didn't figure out what it was. So I'm going to do 1 times 10 to the negative 14th divided by 5.2 times 10 to the negative 4th, which is the Kb, plus the log of, remember this has to be conjugate base over conjugate acid. So the base in here is the reactant side, which is 0.000500, and the acid, oops, sorry, I just put that in the wrong place. The base in here is on the top, 0.000500, and I can do this in moles because it's Henderson-Hasselbalch, so 0.001500 there. And once I solve that, pH equals 10.23888, more numbers. From my Kb, I have 2 sig figs, so that will be 10.24. Okay? All right. Part, you could do the other ones if you want to, but I didn't do them because it's just a whole bunch of the same kind of calculations. So part F is at equivalence. And so this means that I've added the same number of moles of H plus as weak base present. So if I need to refigure that back out again, I can, but I figured out that 20 milliliters was at equivalence. So this means that the moles of H plus added will be the 0.002000 moles, just like what I started with. So I'm going to write my equation again. CH3, CH2, 3 of them, N yields CH3, CH2, 3 of them, NH plus. I'm going to set up my BCA chart to prove what's in there. And you may be able to take shortcuts eventually, but no shortcuts right now. And this is going to be 0.00200 for both of those, which means they both run out. So we're going to use all of that from both of them. And we're going to add 0.002000 on the other side. And these will both be 0. Okay, so now all that I have left in my flask is my weak acid. Everything else is gone. So this means that I have to ice it, which means I need molarity. So the concentration of the weak acid at this point will be 0.002000 moles divided by my new combined volume. So I started with 20 milliliters. And added another 20 milliliters because we decided that was how much we added, or that's what they told us at this point. And so that's a total of 40 milliliters if you're doing it that way, total. And that gives me a molarity of 0.05000 molar. Weak acid, right? So now, because it's a weak acid, I need to ice it. So CH3, CH2, 3, NH plus water. I'm going to write my acid dissociation. It's going to give up the hydrogen, so that's going to give me hydronium and the weak base again, CH2, 3N. And ice, remember, is in molarity. So I'm going to put in 0.05000, and that's all that's in there because everything else was used up. Minus X, 0.05000 minus X, plus x gives me x and x. And Ka, which I still haven't solved for, will be 1 times 10 to the negative 14th divided by 5.2 times Kb, which is 5.2 times 10 to the negative 4th, equals x squared over 0.05000 minus x. We're going to cross off that x. I'm going to do the math, cross multiply, take the square root. X is now going to equal hydronium. And that equals 9.805806 bunches of numbers times 10 to the negative 7th. I'm going to take pH is going to be the negative log of that, which is then 6.00851667. And I have two significant figures from Ka or Kb at this point, so pH will equal 6.01. All right. And then finally, the last one here is after adding 20.05 milliliters of H plus or HCl, and this is past equivalent, so I need moles of HCl, which is going to be the 0.02005 liters times 0.1 molar, which gives me 0.02005 moles. 0.00205 moles of H plus, and I'm going to set up my BCA again in moles, so this will be H plus. Remember, when you're doing BCA, this is always your one way, so I'm going to write plus the weak base gives me my weak base with the hydrogen added, and this is 0.002005. I started with 0.00200 moles, always in moles in BCA, and none of that. And then now my weak base is limiting, so minus 0.002000 minus 0.002000 gives me none of this, plus 0.00200 gives me 0.00200 moles of that, and leaves behind 0.005 moles of H plus, a very small quantity. However, we can see that this really small quantity of H plus is a strong acid, so I can ignore my weak acid, because if there's a strong acid present, the weak acid won't be able to ionize very much. It will be a very small amount past our sig figs. And now I'm going to figure out the concentration of H plus so that I can find pH. So this is 5 zeros and a 5 moles divided by my new volume, which was the 20 milliliters that I began with, plus another 20.005, so 20.005 milliliters, or 20.02005 liters. And I get a molarity of 1.24843 times 10 to the negative 4th, really small quantity. But pH will be the negative log of that, so that comes out to 3.90363 more numbers. And I have only one sig fig because of my moles, which after subtraction was really small. So this is going to be 3.90 as a pH. So hopefully this went well. You were able to fast forward through most of it. If not, hopefully the work helped. Come to class ready to really dive into this. This is the last thing in this unit.